Greetings. In this video, this is a short introduction to Taylor series. The point is that Taylor series is basically the option to take a function, let me say f of x, and transform it into some infinite polynomial, potentially infinite. That means that this function, it can be, for example, sine x, but I can also rewrite it as some polynomial, something looking like coefficient a times x to some n plus coefficient or a1 plus a2 times some x to the another power and so on. So it starts with usually 1 or 0 and goes up. It depends on what terms are missed and so on. But in any case, the general point of this Taylor series thing is basically it is called a series because one is able to take a function which is not polynomial function and make it approximated using the polynomial. I'm not going into derivation, I'm not going into very big details, but what I'm showing here is just the formula for it. So the formula is as follows. So one has a function infinitely differentiable at point A, which is the point around which I want it to be approximated the most. So of course, if one takes a function and tries to make it through Taylor series approximation using polynomial terms, then of course it will be on the approximation. It won't be 100% correct. And the more terms one gets, the more approximated it gets. On the lowest interval with the specified value x equals a, that's a value that we'll choose to be approximated the best, the center of that approximation around which it will be the most concrete. And the more one goes out, the more it will actually be not the same curve that is actually tried to be simulated by the polynomial. So the closer one is to this value a that I introduce here, the better. And another thing is that another thing to take into consideration as well is that yeah, of course, one can develop however many terms one wants. One can do one term, one can do two terms, one can do 5 or 10 or 20. So it depends on the amount of terms, the degree of concreteness or the degree of accuracy to which this approximation is. So f of x, well, the general formula for this is n goes from 0 to, or let's say already to infinity, so whatever very high value is best. So f of x will be equal to such polynomial of the follows form of the nth derivative of f of x minus a, sorry, of a over n factorial times x minus a to the n. Alright, so this is it. This is the general formula for Taylor series, and one can just apply this formula, this sum notation, and develop how many terms one wants. One can do sigma from 0 to 10, or one can do sigma from 0 to 1, or 0 to 3, or 0 to 5, however many one wants. And the a that is plugged in here, the a is the specified point around which we want the approximation to be the best, to be the most concrete. Also, there's a thing called Maclaurin series. Maclaurin series is basically Taylor series with a equals 0. Thereby, this sum notation will be easier. So Maclaurin series is Taylor series around x equals 0, a equals 0. And again, I can write it like this. F of x will be equal to 0 to infinity of nth derivative of evaluated at not a but at 0 over again n factorial times x minus 0, so x to the n. So this will be simpler. Alright, Maclaurin series, Taylor series, but in simpler terms because a is straight out set to be 0. That's the special case of Taylor series. But this is general because one can choose a equals 3 or a equals pi, a equals 5 or something, a equals 22. And in such case, one is able to get approximation best and around that point that is chosen to be a. So just to maybe illustrate this, we can take some concrete function and try to take the exponential. It is most probably most efficient to try this out with e to the x or e to the 2x or e to the x to the second or something in that case, in that sense. So let's say that I want to try out this Taylor series expansion. I want to say, let's say in this case, for the easiest one, I will say a is 0, so I will evaluate it at 0. Alright, so we want the approximation of e to the x around the point 0, and basically the point will be I want to say that e to the x is equal to this Taylor series, and I want to develop, let's say, the first 5 terms. So a will be 0, first 5 terms I will do. So these two informations, a equals 0 and first 5 terms. Alright, so what that means is I will do exactly that. I will use this sum notation and develop the first 5 terms. The first 5 terms means n equals 0, n equals 1, n equals 2, n equals 3, n equals 4. Alright, so for n equals 0, what I will do is, it will be, first term will be the 0th derivative of e to the x. So what is the 0th derivative of e to the x? It's just e to the x. So e to the x evaluated at a, but I said that a is 0, so evaluated at 0. So e to the x is e to the 0 now, over n factorial, now it's n equals 0, so it's 0 factorial, times x minus a, but a, again, I said it's 0, so we're actually using the Maclaurin right now that I mentioned as well, but it's now deleted at this place. X minus 0 to the 0 now, because n is still 0. So this is the first term, the n equals 0. Then for n equals 1, well, is the nth derivative and evaluated a, again still, we're doing a equals 0 for all 5 terms. As I said, in this case, we're just trying out a equals 0. So if a equals 0, that's been done. Now, a equals 0, n equals 0 has been done, this first term. Now we're doing n equals 1. So the first derivative of e to the x, why it's a good function to choose for this is because it does not change with the derivative. It's still e to the x. So it will be e to the x evaluated at 0 again. So again, e to the 0. Alright? Then over n factorial, now it's 1 factorial, times x minus a is still set equal to 0. It will be set equal to 0 throughout all this example, throughout all the 5 terms that I said I'm developing here. Then it's to the nth power, which is now 1. And then I continue like this. It will be e to the 0 again, over 2 factorial because it's n equals 2. Then it will x minus 0 to the 2 because n equals 2. And then I continue with this 3 factorial, x minus 0 to the 3 plus, and the 5th term, as I said, 4 factorial, x minus 0 to the 4th power as follows. And now this can be simplified. One can simplify this 1 over 1 times 1, so this is 1 plus x plus x squared over 2 factorial plus x cubed over 3 factorial. It's exactly the same expansion that I had mentioned in one previous video, in which we talked about the expansion of e to the x to the second order to take a definite integral of it. So that was the point there. Alright, so this is the expansion of e to the x around x equals 0 at the a equals 0 case. So this is another example. Now, this can be done for different functions as well. This can be done for sine, cosine, or whatever. One can expand sine, cosine as well. One can also expand ln, one can expand, really, if the function is infinitely differentiable at the chosen a, can be created this Taylor series. So, for example, for if one wants to do the Taylor series for sine x, well, again, this thing will apply. And let's say in this case, I will not use 0, but I will say a equals pi. So I want to take the approximation with the best approximation being at x equals pi. Therefore, I said a equal to pi. This is the point. This a that comes here can be 0, but then the approximation is best at x equals 0. If I want to make it best at x equals a, I'll put the a there. So now, again, using this same rule, let's say I want to develop the first 5 terms again. Alright, so let's do the same, just with a equals pi in this case. So if a equals pi, well, this same thing applies now. So first of all, the 0th derivative, that's purely sine, and it's evaluated at a, at pi therefore, over n factorial, it's 0 factorial times x minus pi to the 0th power. So this will be also 1. Alright, so this is the first term. The second term will be the first derivative of the function, which is sine x prime, that is sine prime of x, that's cosine x. So cosine, and again, evaluate the derivative at a, which is pi, so pi, over 1 factorial this time, because n is equal to 1 now, x minus pi to the first. So that's the second term. The third term will be again derivated once again. The second derivative will be minus sine evaluated at pi over n factorial. This is n equals 2, so 2 factorial times this thing. X minus a is pi, still the same thing, to the second. And this continues. Now further derivate minus cosine of pi, the third derivative, right? The second is just the third derivative of sine. It goes back and forth. Therefore, it's easy to derivate as well. Over 3 factorial times x minus pi to the third. Plus, to do the fifth and last term, this will end up being sine of pi. Yeah, cosine prime of x is minus sine of x. Therefore, minus cosine of pi, that derivative is going to be sine of pi over n equals 4, that means 4 factorial down here, and x minus pi a is pi still to the 4th power here, to the n power. Alright, so these are my first 5 terms for this expansion. Now this can again get simplified. One might find a pattern here. Usually in these expansions, in these quite simpler functions or more common functions, there are tables for them because there's patterns that have been found. There's patterns in the e to the x, there's pattern for the ln x, or usually it's done ln of x plus 1 due to the problem of evaluating it at 0 when the derivative is 1 over x. But in any case, I'm not going into that concrete example now, but just to wrap up this video, what I'll do is maybe simplify this at least slightly. So what we've gotten is this is 1, this is 1, so it's sine of pi, which is, okay, so we might first try to just give the sign and then figure out what those are. So sine of pi plus cosine of pi times this thing. Well, it won't be that nice, so this will be times x minus pi, just taking out, this is 1, this is x minus pi, simply cosine of pi. Well, cosine of pi is minus 1, times minus, okay, so this can be evaluated, this will be 0, because sine of n pi is 0. Alright, so then the third term is this one, minus sine of pi, that's minus 0. So this term actually goes out because it just multiplies it. Therefore, this thing also should go out actually. Then minus cosine, so just the cosine terms will actually be counted. So minus cosine time, the fourth term, well, so it ends up, this is 0 again, so it ends up actually out of the 5 terms we've gotten, only 1, 2 will actually appear because the rest actually go to 0 due to the value of a, and due to the value of a, and due to the fact that sine at pi or at 0 is simply 0, and those terms all go to 0 therefore. Alright, so plus 0 for the third term. For the fourth term is minus cosine pi, which is cosine pi is minus 1, therefore minus cosine is 1, so it's 1 over 3 factorial, which is 1 over 6, times x minus pi, all of that to the third. Alright, so this has been taken care of, and this last one, again, sine of n pi or sine of 1 pi, 0 simply. So the end result here for the first 5 terms, systematically it's the first 5 terms, realistically it's just 2 terms done, right? Because all the other ones go to 0. So the only thing that will appear actually indeed is this part. But in any case, this is still nice to see how this works. And one can do this, as I said, for functions infinitely differentiable at the point x equals a. It just works very nice. And of course, the accuracy goes down as one goes further away from this point. But in any case, this is kind of an introduction to it. Hopefully you'll also try it out.